Now we begin the process of repair. And the usual question is, where do we start? No matter what kind of problem it is, what do we do first and why? The answer is simple. We study the board. We carefully analyze its condition and construction. It's a process we call reading the board. And it consists basically of asking and answering a series of questions. We read a board just as if it were the page of a book, filled with all the facts we're going to need before we start. What kind of board is it? Is it made of epoxy, ceramic, mylar? What type of circuitry does it have? Is it single-sided or double-sided? And if there's a coating on the board, what kind is it? Is it thick or thin, hard or soft? What are the solder joints like? How close together? What's the lead to hole clearance? Has the board been damaged? Are there any burn spots or broken resistors, perhaps? Before we even begin to take it apart, we need to identify all its basic materials and see how it's been put together. So let's start with the base material, sometimes called the substrate. This particular one is a laminate of epoxy and glass fiber. A number of different kinds of substrates. The one used depends on the application. Tan ones like these are made of laminations of cotton or paper that's been impregnated with a phenolic resin. They're inexpensive and used for moderate temperature applications. They're not as rigid as epoxy glass. This one's designed for very high temperature. It's ceramic. Usually these are white in appearance or light tan. Most boards are rigid and designed to keep their shape, but some are purposely made of thin, flexible material like this. They can be formed to fit the available space. The commercial designations for the various types of base material are listed in your handbook. The reason it's important to recognize what type you're dealing with is that it tells you what the heat and mechanical load limits are. A hot iron pushed down on this ceramic board probably won't hurt, but do that to a mylar flex circuit, for example, and you'll burn a hole straight through it.
The second main element of a printed circuit board is the circuitry itself. It's made of a conductive foil, usually copper, that's been bonded to the base material. The two most common types are known as 1 ounce or 2 ounce copper, based on the weight of a square foot of the foil. 1 ounce copper is 14 ten-thousandths of an inch thick, and 2 ounce copper is 28 ten-thousandths of an inch thick. The metric equivalents are 0.035 millimeters and 0.071 millimeters. The trend is toward using thinner and thinner copper. In multi-layer boards now, you can find half-ounce copper with a thickness of only 7 ten-thousandths of an inch. The important thing to note here is how extremely thin the copper thickness is in comparison to the board itself. It doesn't take much heat and pressure to cause the foil and the base to separate. The circuitry consists of the conductors, sometimes called runs, the lands or pads, ground and voltage planes, and the heat sinks, so called because their large mass helps to dissipate heat. Ground and voltage planes also help dissipate heat. Now let's look closely at the holes in the board. This is a single-sided board. It has circuitry only on one side, and the holes are drilled through, but there's no electrical connection between the two sides. Holes like these are called unsupported holes. On this double-sided board, the holes have been lined with copper, so they electrically connect the two sides. These are known as plated through holes, supported holes, or through connections. Another way that through connections are reinforced or sometimes originally made is with an eyelet or a funnelette inserted in the hole. They're usually made of pure copper and plated with solder or pure tin. The need to get more and more circuitry in a smaller space has led to the development of multi-layer boards. They're similar to double-sided boards, but have one or more additional layers of circuitry sandwiched inside. In some locations, the plated through holes connect to these internal layers. At other locations, They do not. And this is a vital thing to know when you're removing a lead from one of these holes. The internal planes can act as a heat sink, soaking up so much of the heat you're applying to the pad that the joint never melts all the way through. Excessive heat, on the other hand, can damage an internal plane or cause discontinuity, often with no outward sign of damage. So heating is a critical operation that we'll have more to say about in the lesson on component removal. The components themselves come in a wide variety, but can be classified into general categories depending on their function. Resistors, capacitors, diodes, transistors, and integrated circuits. The leads of the components are terminated in 6 common ways. This is the straight-through or unclinched lead. It's the easiest to remove because there are no bends after they pass through the hole. The clinched lead. It's usually used to stabilize the component so it won't move during soldering. The semi-clinched lead serves the same purpose, and it's easier to straighten out for removal. This is the swaged or spaded lead. It's been flattened to increase its width and thereby hold the component in. It's not easily removed. Surface mounting is used with components like flat packs. The leads are soldered to pads on the surface and don't pass through the board first. A variation of this is called offset pad mounting. The lead does pass through the hole and is soldered to an offset pad on the other side.
So now we know some things to look for when we analyze a board, because they're going to affect our strategy in dealing with the repair problem. Let's add 2 more considerations. Take a look at these 2 boards. What strikes you first about how they differ? This one looks like an easier one to work on, and it probably is. The components are widely spaced and easy to get to. We'd say the board has low-density packaging. This one is something else. The circuit runs are much narrower and closer spaced. Through-hole lead clearances are tighter, and some of the components are mounted so close together that they're virtually inaccessible. High-density boards like this often require you to partially disassemble the board to get at the component you want to replace. You have to literally demanufacture first, and then remanufacture it with the replacement parts. And finally, there is the possibility that the board has been coated, covered with a thin or thick material to protect it from any number of things. Coating removal can be a major problem in repair, so we'll devote an entire lesson to it later. How to identify each of the types you're likely to encounter, and what methods to use for removing them. We're going to cover all this in detail as we progress. The important point to have in mind now is that your first step in every repair problem is to study the board itself. Analyze what's in front of you very carefully. We read the board. Suppose, for example, we get a board like this one. A dual inline pack went bad, and someone who didn't know how tried to rip it out and left you with the result. What can we tell about the repair problem just by looking? Damaged circuitry and several lifted pads. What type of board is it? A double-sided one. Reasonably low-density packaging, so it's easy to get to the joints. What type of hole support and thermal mass is involved? They're all plated through holes. This one, though, is connected to a large ground plane, so it's going to require more heat than the other joints. What about coating? The board doesn't have any, so we'll be able to skip that step in the repair process. How about the base material? It's an epoxy glass, so it has a relatively high resistance to heat. And what type of solder joints are there? 2 corner leads have been partially clinched. We'll have to unclinch them during desoldering. Questions and answers. As we read the board, the vital first step in the process of repair.
You'll find a full presentation of what we've covered in your handbook, so we'll stop now. Your instructor will want to review the material with you, and in the notes section of the handbook, have you write in the particular specifications, standards, and practices of your organization. Then we'll move to our next lesson, component removal methods.